Good evening, mathematicians and lay math enthusiasts. My name's Jeff Cook, and joined with Greg Volk. Denny couldn't be on
Howdy.
today. Say hi, Greg.
Hi.
I was doing something neat. Well, let me just introduce. This is a direct proof of the Riemann hypothesis, and it's been 4 years since we put a preprint up. Happy anniversary! It was this month or last month.
hmm Well,
And we found an error. Yay! Actually, it's an error that some people have been saying already was an error. I've never not had it explained with the specifics of the paper. And it was interesting. I was going to pull up the paper here, and I came across this on Brave. Oh, by the way, it was an easy fix, so it's okay. Right here. The proof appears to contradict established theories and mathematical frameworks. All right, I'll get into that. All right, so the it can be proven by simple algebraic manipulation. Okay, that's kind of an issue. That's what we're going to get into. That would imply that there are no fields for which the Riemann hypothesis does not hold, which is not the case. What they mean is that if you get any step in the proof where you set the Riemann zeta function to 0 and it reduces to a simple rational, manipulation, then you can substitute other functions in if you're not using any properties of the Riemann zeta function, and that those functions could have zeros off the critical strip, and you can continue on with the proof. I think that's
mhm,
very questionable, but everyone keeps doing it. And
right.
so I acknowledge and kind of went over, we see the problems in that is that should be, the final result should be standalone. So the behavior itself of the zeta function should end up at 0, and that should be the final step. Once you start
Right.
manipulating after it turns to 0 and you rearrange, you're just left with a simple algebraic expression, and
hmm
some harm can come. And I'm going to explain that in a second. So, but anyway, how to get the paper? You want to go there? You can go to your favorite search engine and click on Jeff Cook Riemann Hypothesis. Dennis Allen or Greg Volk also brings it up.
hmm
So almost 15,000 reads. Maybe we'll top that over after this video premieres.
Yeah, let's hope so.
This has been updated, and I will give the actual statement. I don't know where to find the comments. Maybe here. Ooh. Yes. Okay. So the revisions of this draft reflect changes in response to a counter argument, and then we go on to what I just kind of said. Um, we concede this substitution should not be permitted. Meaning we should not be able to substitute another function in place of the zeta function anywhere in the proof. And
Mm.
so it's kind of a high bar, but it is a difficult problem. So it seems that we should follow that, and we do want it to be accepted, and
hmm
of course we don't want any errors in it. So it has been argued well, and there's a number of people. I'd like to give you a shout out to all of those who have brought this up. We appreciate it. It's made the paper better, which is the reason why we're doing these videos. This is our way of getting peer review. We also email mathematicians as well. Um, and we do have papers contact us.
hmm
Greg and Denny just got one from journals that want to publish it. But Greg, I looked into that paper, that journal, and they're not reputable enough. They're big.
Okay.
They have a lot of people, a
Yeah.
lot of papers, but
So yeah, I get it. To be
they're
clear,
not in the
a
circle.
journal
That's all.
approached us offering to publish the paper in their journal, and we're probably not going to pursue it.
No, I've gotten in the past 3 years about five, and they're all similar. They're all kind of, we're already the pariahs. We're not in academia. We're
Yeah.
not in their circle. And so other journals um, that are going to offer that, it doesn't move anything forward, not for
Right.
us nor for mathematics on a whole. It has to be accepted by the mainstream mathematics, or I'm very happy to leave it on ResearchGate. That's fine. I'm good with
Yeah.
ResearchGate, and we can get it. All right. Anyway, so
I
argue.
wanted to
Yeah,
make a point on
please.
that, but
Yeah, go ahead.
at some point you wanted me to give a summary, and I don't know, this isn't necessarily a summary, but more of a history going back. I mean, Jeff's been working on this problem longer than I have, probably 20 years plus, right? Um,
Yeah, yeah.
and he introduced me and Denny to it probably, I don't know, about 6 years ago or so, and we worked on it some. And during the course of that time, I remember being presented with the idea and thinking it through. that rather than prove that the zeros are on the, the line one, real part 1/2, let's find another function that has the same zeros as the Riemann function, and we can prove that it has the same zeros, and then we can from that prove that this other function has to have real part 1/2 or imaginary part 0, and which are the trivial zeros. And so that I thought that was a really clever approach, kind of what we were going. And now we're kind of removing that, but that's actually how, at least as I understand it, that's how the whole thing started. Is that how you remember it, Jeff?
That is, and we're still using shares all the same. The alpha function upsilon. We're still using
And
alpha.
it was
Yeah.
this idea that allowed you, Jeff, to develop this thing which you call the Riemann oscillator,
Yes.
which is nothing more than it's like the function, the zeta function is equal to something else which oscillates. It's just a second order polynomial equation, and it has a variable. There's the variable s, obviously, but also a variable t that changes with time, and we just then let t approach 0 to get the result that we're looking for. And it does seem like, why are we going all out of our way to do this? But it does turn out that it bears a lot of fruit. And I just wanted to also say that the original paper was like 90 pages long. And it had all this, stuff about the Riemann oscillator in it. And, Denny and I kind of advise you, none of that's really absolutely necessary to be able to prove the hypothesis. And so we ended up with a much shorter paper. And, but the Riemann oscillator was always an essential part of it. And I do feel like it's kind of people who are reading the paper and not seeing that all of that background are missing out on that. So what's also new is Jeff just showed you he's starting to use GeoGebra, which I've been using for a while, and being able to make an argument just based on geometry, I think is beautiful, and that's what we're still working in that direction. But anyway, that's a little bit of the history of what's going on. So
Very
back to
good.
you.
Yeah. Thank you. So here is the oscillator equation. It's equation 2. But let me go. Let me
Can
find
I just, before you go too
Yeah,
far,
please
notice
go.
that it's a function of s and a function of t. So there's
Yes,
two
we'll come back to
variables.
that in just a second. Let me find it on the other paper. Um, Probably here. Yes, the longer version. So this is not the 90-page one, but it does include all of the research.
There've been
And
about, I don't know, there've been 100 different versions over the years of this
yeah, I
thing.
have all the copies in
Mhm.
case anyone wants to see. Well, you changed this. I have all the copies saved. But it's the same idea as we're going to build the oscillator part by
Mhm.
part. The longer version has the steps where we're building it, and then we graph it every step along the way. And
Mhm.
so we then build other parts. And this one's important because it has this diagram that we're building. We're graphing the oscillator in phase space is what it's called. And this is
So t represents the variable for phase space.
yes.
Usually it's the other way around. When
Exactly,
t
but
is
it's a little
time, it
different.
has
It
this
become more beautiful. It was
phase.
more beautiful this way, I think, and you get
That's
more
fine.
information. Yeah.
Just
All
want
right.
to clarify.
Yes. All right. So this is the final image, and a lot of people look at it and go, "I don't understand that," and so they move on. But
Right.
this is the way I always look at the Riemann oscillator. Now is the way I look at the zeta function because it has all the components of the zeta function, and this is what we turned on. So I'm going to what I mean is turned on is we do it in GeoGebra now, and it's just as I was kind of going over the proof, and I wanted to see what step did we lose everyone. Let me just go do that really quick.
Where did we lose everybody?
All right, because that we can't have it, it's defeating the purpose, right? So, um, I think it's this one. All right, so here's the latest draft. All right, so it's equation. This everyone agrees is very good. The construction of the oscillator works. It's very nice, and there was a step we took out, but it was right around here, like equation 18, where we
Mhm.
set the zeta function equal to 0
Mhm.
And then it left this rational expression in terms of upsilon. And they said, well, we can
Just to be
turn,
clear, you mean t equals 0, not s equals 0.
no, sorry, yes, we let t equal 0 and we get
Right.
18.
I
Sorry.
understand. I know that. I'm just explaining that
I
just
appreciate
so
that. All
people
right, so it's
understand.
17, yeah, 17 at t equals 0, the function becomes the zeta function. Now, when we let the zeta function equal 0, this is where we run into the problems.
Hmm.
Because we let the zeta function equal 0 and we solve back for upsilon, anything after that was suspect to all the other mathematicians, or not
Hmm.
all of them, but some of them. Okay,
Hmm.
and that's the issue, because then we're just left with upsilon. Let me get it, show you
So
exactly
now
where.
instead, we're waiting to set t equal to 0 until much later in the proof.
The very
That's
end,
basically the
as the very
difference.
end, the properties of the zeta function will send it to 0 under the
Hmm.
conditions met. All right, so let me go and see if I can find.
And a little more
Please.
history while you're searching.
Hmm.
You may have noticed in that he mentioned the Abel-Plana formula, and I believe, Jeff, correct me if I'm wrong, but I believe the Abel-Plana formula was the function that kind of hinted towards the Riemann oscillator in the first place. The
Yes,
fact that you
yes.
can express the zeta function as this weird expression um, sort of implies that maybe we could express it in as a derivative of something, a second order polynomial, because it has three terms, and
Yes.
then the higher order, the square term and the unitary term go to 0, and all that's left is the one in the middle. And anyway, that's kind of the idea where we were trying to go with this whole Riemann oscillator, but it's just it's so rich with implications and ideas that stem from it that I think the Riemann oscillator in and of itself should be studied by a lot of people as much as the Riemann function itself. That's my opinion. I have a very high opinion on this,
I agree. I agree. In fact, there's something neat I want to do at the end. I want to talk about
and
the end. So
I hope we
remind me
can
of the
express that to people how what a treasure this can be.
yeah, exactly. For the mathematics community, it's like kind of having the quadratic formula and no one's accepting it. It's like, think of all of the things you're going to be able to do with this in the future, but you have to
Right.
understand it. All right, so let me show where the step is where we made error and why it's not the issues anymore.
Okay.
So, all right, let's go over. It's got to go over it right
Okay.
here. All right, we we got the theta function. This is equation 18 in the new draft. All right,
Mhm.
lemma
This
2,
this is
unnecessary
the old
anymore.
draft you're looking at right
This
now,
old draft,
correct?
yeah, this is the long version. Old draft still up there.
So
I want
lemma
you.
2 and lemma 3 are just basically eliminated.
They're eliminated now
We don't
because
need them.
yeah. So this is what we're doing is we're setting the zeta function to 0. This at 4.
At t equals 0. Got to keep
No,
saying that.
zeta function equals 0.
Oh, setting this. I'm sorry.
See
Okay,
see
the zeta
equation
function.
4.
Okay, yes,
All
I
right, we
do.
already set it, and that's okay. You can set it to 0 up there. That's fine. It's just when here when you set the zeta function equal to 0 and solve back for upsilon, you're left with just s. This is a rational algebraic expression. This is the problem where now you can substitute anything in there to show functions that do have zeros off the critical line, and therefore you can. It's saying that this proves nothing the moment we do this in this step, and yet we continue on to do other things. So what we need is a condition like this, where we're done when we set it to 0, and not setting upsilon equal to 0,
Hmm.
setting the zeta function equals 0. So here we go to set the zeta function to 0, and then we don't let upsilon equal 0. All right, so this is the change. Let's kind of go over it a little bit, but first
And just to
let's,
be clear,
yeah, go ahead.
in the oscillator, the upsilon function is kind of like if we have a second order derivative, the coefficient of the the first order would be the upsilon function. So it's kind of like the resistance function. It operates in the same way to the Riemann oscillator as a resistance function would to a second order a driven oscillator.
Or
Hope that makes any
damping,
sense.
or
Or
yeah,
that's what I meant. I said
yeah,
resistance, I
that's
meant
okay.
damping.
And
Yeah.
then
So
what's really interesting also on this too is that the alpha function, which is a bit simpler than the upsilon function, is simply a multiple, or is it divided by the frequency, the fundamental frequency of the oscillator? And
mhm.
so you can, and that's the decay rate. So if you think of the zeros as a zeta function, we're very much interested in decay. So the original paper, 90 pages, was all about exponential decay. And so we're interested in how the Riemann hypothesis, or the Riemann zeta function, decays to zero, is the way to look at it. And instead of using upsilon at all, I found that, well, you could use upsilon, but alpha seems to do it a little bit neater. It's just less variables. But this is what it looks like with the oscillator, that image, when you kind of get it going. All right, so this is everything that's happening with the oscillator. You were talking about the derivatives. So this is the second, or this curve here, this green line. Do you see my cursor, Greg, moving?
Mm-hmm.
Yeah. So
Yes,
this green line are all the infinite points of t. We got t up here, and at this point, the t is not equal to zero. So is t equals zero?
By the way, that point that's ahead of the point that's point F that's, or point T that's moving, that would be the derivative. It's the point.
Yes. So this
It's
is
the direction the things are going at that point.
Yeah, this is, well, a second order derivative, actually, this particular one. But you can actually plot any of the derivatives on here. So, and then this point here is the minus Dirichlet eta function. And we're going to get into that a little bit. We just call its points z of t and s. All right,
Just want to point out, if we know the eta function, we know the zeta function.
Yes, it's very easy to get that.
Related. That's a no-brainer.
The reason we use the eta function is because it converges, the infinite series form of it does converge between, when the real part of s is less than 1, between real part, or 0 and 1. The zeta function only converges, this infinite series only converges when the real part is greater than 1. So that becomes easier to plot on this graph. So the zeta function, you'd have to take it into 3 dimensions to represent it. But the eta function is simply a multiple of the eta function. And the exact value is somewhere in here. But, all right, so essentially what we have, if you're unfamiliar, you can go watch the other videos. It describes this diagram, but we're going to break it down a little bit more as AI has come into the picture, and it's a useful tool, especially ChatGPT 4, as it gets better with its math and is now accessing the Wolfram, or the mathematic engine. Is Wolfram engine is what it's called. They teamed up. It's become very good at checking certain things, and far better than 3. And it was looking at this diagram. I plugged it in, and it's saying that it's already proven just by the diagram. And I'm going, I said, I don't know what you're talking about. And it came to a point that was, oops, I don't have, oh, hold on.
Can I just point out just the obvious, because not everybody's going to know. The obvious is that I want you to go back to your diagram. There are basically 2 functions, s and t. Now, s is composed of a real and a complex and an imaginary parts, which he calls a and b. So a, which is the real part of s, has got to be a half in order for the Riemann zeta function to equal 0. So, or b is equal to 0, and they've got what are called the trivial zeros.
Yes,
so s
so
and t
I
are
have
the only
real
variables.
part.
Everything in the diagram is a result of s and t. And we're looking at a complex plane here. So
yes, so this is the real line, 0, 1, 2, 3, minus 1, all that, and then the imaginary going up and down. Okay.
just want people to get that.
All right, so we have s is the argument of the zeta function. And this entire shape of this structure changes. So the circle gets better. That's a fixed equation. And b is the imaginary part, and it changes. And we're going to really dig into it here. But let me just kind of show what I was describing, each part I was having the AI doing it. And this is what it's saying. As you take t out, so these are the infinite number of t's. And if we only consider the natural, and this was discussed in the first paper, so this was information I was given to the AI at first, but I want to tell you what it shared, is that all of the points, the natural arguments t, as we get closer to 1, it's going to plot a point. So let's go back to here. As we go out, and we're at 1.35, it plotted in an ugly place. I can't see it with all this stuff going on. There we go. Well, let me move that That point right there. So there's the first point, natural
Which point?
argument,
The point R?
right below that my mouse, my cursor is pointing to. Do you see it?
Oh, okay. Yes,
That
that
point on
point
the
doesn't have
blue
a name.
spiral.
Okay.
That point there. Now let's go to 2, and it's where is it? Follow it right here down in the lower right quadrant. And as we go, what we find is that it's always for the zeros, it's always going to evenly distribute them so that they cancel across the quadrant.
Can I
All
just
right.
back up a second, Jeff,
Yes.
just so you don't move too fast? Each of those points corresponds to a time when when t is an integer. I know you probably said that, but
Natural numbers, is what I said, because
natural numbers. Okay.
yeah.
So when t is an integer, we're going to plot a point along this blue curve.
Yes.
Okay.
Right now we're we have
I just
3
want to
of
make
them.
that clear.
That's fine. So here's the first one, and it kind of goes around. Here's the second one, and here's the third one. And they're all going to be equally distributed around. So if you're at a certain point, and if they're going to go, if the zeta function is going to go to 0, they're all going to cancel. So this quadrant is going to cancel this one's going to quadrant this one, and it can't converge too quickly. Otherwise, you'll have all the points on one side. For example, if we take this, you see there all of the points are kind of in the lower left-hand corner. And there's nothing all around the rest of it. And this is clearly not potential for 0. And it's not that they cancel each other exactly, but they cancel a large enough piece of the sum that it keeps going to 0 and 0 and 0. So to do that, as the spiral, as t moves forward, you have to kind of make sure that they're all evenly distributed in general. So there is what AI saw in this is what I saw, but I didn't see a proof in it. And let's kind of go back. Is that it has to do, well, I knew it had to do with this line here. So this point S, and this is the second order derivative f, so it's 1 over s minus 1 when t equals 0. Now, when these are lined up, that is the number one point where you get the 0. It's this number one potential for it. This is a requirement. They have to be 1/2 that these lines line up in order to get it. Now, there's another
That's
condition.
easy to show algebraically.
Yeah, we're going to show in a
the
little
only
bit.
time that they line up is when the real part of S is a half.
Yes. Now, so for the zeros, which I have them on here, I'll get to them in a little bit. So let's see. But as you see, it gets very complicated, and so it's difficult to see everything. So a couple of things before we move on. All right, so this derivative is very important. So the t it takes to get from here to the imaginary line is the arc length from P to L to, I was in the wrong circle, L to R, right there, R. And so this, on this
that's
brown,
the brown circle, just to be
brown, yeah, this arc length here parameterizes this arc length on the curve. Likewise, this arc parameterizes this length. And you can solve that algebraically easy, just kind of you express things in parametric equations. So that's very important too, because the derivatives, are kind of set in the motion for the zeta function itself. We'll get into that a little bit. But if this is at one point, so there we can. Jeff, can you
just take a minute?
Yeah. Well, let me finish this sentence here. It only equals this. It only equals that arc length if the real part is 1/2. So it's very important. So this is the time. So if we I'm gonna hit play, then you see it's kind of like a clock. This dot here is kind of like a clock going around, and that is setting the lengths of all the rest, particularly the tangent angle coming out on the spiral of the zeta function, which I can actually, before you ask your question, I can show that line. Well, go ahead and talk while I'm finding it.
Well, all I wanted to, you said this, you said the one little curve from from the real imaginary axis to F parameterizes from J to R. And then you said a couple of things. I just want you to define what you mean by parameterizes. That's all. It's not.
Yeah.
It's not
So the
equal.
other way to say it is that it maps. You can map one point to the other
Okay.
if they were surfaces. So you can express it in terms of mapping. You say,
Not that they're equal, but
no, they're not equal.
there's a
But you can
one-to-one
actually
relationship between them.
exactly. So all right. So then let me find. So we'll say yeah. So let me bring this time back further. All right. And then again, that only occurs when the real part is 1/2. So if you think of it, if you look at this spiral here, this blue line,
Mhm.
it kind of stretches. It's like a spring. All right.
Mhm.
So it kind of coils as we go to real part 1.
Mhm.
It curls too much. And you see then there's this imbalance of the dots here. See, they're all kind of here and then here. They're not, and it happens too fast. It spirals inward too fast. It converges too rapidly, I guess you could say, and for it to cancel out. Now, if you go to real part equals 0, the far extreme, it's just on a circle. So it goes around and around and around, and
They
that
don't
doesn't
cancel
converge.
here
It
either.
doesn't, yeah, it doesn't cancel enough. So that balance between complete circle and I think it's logarithmic curve, I'm not sure, but it's very,
Mhm.
very rapid curve,
Mhm.
is right there in the middle. So that doesn't, in my opinion, it doesn't prove anything except what we're going to show in a little bit. All right, so,
Right.
but it tells you why the zeros exist in the first place, because the points across quadrant are canceling each other enough. Now, I did want to show the tangent angle. This is where AI was jumping up and down. It was really neat. I got it. It was really,
AI got excited.
and it defended it vehemently. I said, no, I don't think so. And it's like, it doesn't. I'm like, okay, I think you're wrong. It really is saying that the proof is already here. And it went on to explain it. And I have a long thread. But so I can't think of all of these geometric relationships all at the same time. And AI has a different way of processing because it knows all of the definitions. So
Mhm.
Greg is going, but I went through algebraic. This is what it said. It said this point here, B,
Mhm.
this was the error or a misunderstanding of the original paper, is that I thought we defined B, the distance 0 to B.
Mhm.
And with that, that has the condition where
It's a function of S. It's determined by.
yes, but S actually it can be derived. And AI derived the length of B geometrically, and I didn't do that. I slipped onto it before, and that's where we always get those interesting properties with phi and golden ratio and all that with that
Mhm.
too. But it's that distance in the paper, and it's still in the long form. It says that this is we are defining it to be this length to have this relationship, but believe it or not, it actually has it. So once you have S, everything else about the zeta function, all the way from the zeta function, can be built step by step, and the proof also follows by implication of geometric relationships, and we're going to show. Greg is also working on, and I got a little surprise at the end. If you want to earn $1,000, I got something for you for whoever wants to do it, because this proof is, when we get to it, when we show it, is very, 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 very good.
I want to earn $1,000. What do I have to do?
Finish your GeoGebra thing.
Oh yeah. All right. Well, okay. I didn't know you were going to pay me $1,000, but all right. I
Well,
won't
it's
make you pay me.
no. It has the
I will
condition.
finish it.
It has a condition that this proof has to be. We have
I
to win
will
the
finish
millennial
it.
prize first. I don't have $1,000
Yeah.
to hand out. But if we win it, I'll give $1,000 out of my money for anyone that does something with this, because I'll
Right.
get
Well,
it. I get it.
I'm definitely in line to do that, and I have a feeling I'll finish before the prize
Before it gets
comes out.
success.
But
Yeah, but I'll kind of
I'm not holding my breath on that one. But who
no,
knows?
exactly.
Could
But
be.
you never know, because this one is pretty. I mean, enough mathematicians dug into this proof so
Yep.
far, so
Yep.
they're going to be digging into this,
Yep.
and
Can I
they're
just?
not going to be able to do. They're not going to be able to look where they were looking before, because what we're going to show is So obvious. It's very, 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 very obvious. And I'm going to show it very soon. But go ahead.
Yeah.
I'm going to show.
Well, I just want to say,
Go
you know, the AI did give you an inspiration, and that inspired me too. And that is, geez, can we do this whole darn thing just
Yeah.
graphically?
A single image.
How cool would that be?
It's
If we could
saying,
just
yeah, it's
say,
saying,
this
yeah,
is proving
it's saying
right
it's
here.
already proven with this diagram. It's just
Yeah,
where I'm not
and
seeing it.
and I'm not quite either, and I'll be honest, but I believe it. You
It's
know, and
it,
so
but
I'm
it can
working
I can
on it.
sit there and ask you questions about it. But if you plug in this diagram step by step and how it's constructed, you can ask questions all day long, and it will
You
tell
haven't
you
shown the
everything.
coolest part of it yet, which
No,
is
I'm
the
gonna get there.
sum of those things. But I don't know if that's where you're
Is
going
that
with.
I don't know. It's just saying what AI keeps saying. It says no. It's like a the exact analogy of this is kind of like a waveguide of light, and so the rays will cancel if at a certain trajectory. So I'm trying to find the trajectory. I think it's here.
It's
Yes.
making me think also that maybe we're on the verge of finding some physical applications, which
Yes,
wouldn't
yes,
that be
yes, yes.
cool?
So it's this tangent. So we got a perpendicular line. We're at t equals 0. So look at the radial line at any point of the or eta
Okay,
function.
there's
We'll
two
just,
lines. Which one's which?
I'm
I'm
going to show. I'm
sorry.
going to show in just a second.
Okay.
The blue line is the perpendicular line. It's going exactly perpendicular to this black radial line.
Okay.
The tangent line, that's called K line. I don't know why it's called that. That's given the angle here. It's given it up here, and it's going to get closer
Right.
and closer to 90 degrees
Right.
as
As you
t
move in.
increases. So you kind
Yes.
of for all s, not just
Yep.
the zeros. Okay, so that tangent line, because its initial, and if you look at the function, we're going to get into it a little bit. If you look at the function of the eta function, it's this tangent line. Because you know the amplitude is going to be 1 at the maximum. You know its initial phase, which is this tangent angle. You know its period, because I'll show that in a second. So you can learn everything about this function just from its initial tangent angle. And so exactly here's the 1/2, and see the tangent angle changes a little bit when the real part changes, and it changes when the imaginary part changes. Okay, so it's at the real part 1/2 is when these lines line up, and
You can think of that as the first order, the 0th order, and the second order derivatives.
Mm-hmm.
When
Shall we show them a
they're
0?
matched, they cancel.
Shall we show them a 0?
Sure.
Ready?
Yep. Oh,
All right, here's a 0.
okay. Yeah.
Let me shut this off. Now you can't see anything here. Got to do a few things.
16. Wait
And
a
I'm
minute.
going to zoom in.
You're not actually at a 0. Isn't it like 14 point something?
Sorry, I didn't go all the way across.
Oh, okay.
I'll do
That's the second 0.
Second
Okay.
0. Because I set it just 2 zeros, so I can just scroll all the
Right.
way.
Yeah. First one's 14 something.
You don't see much here, but when you turn it on, you see everything. But you got to zoom in. What you'll notice is that we have the points. I have put this pink circle on the individual points, and then the red circle is the actual sum of the points. And so you'll see after it's summed, it's going to shrink to the next 2. It changed size. Let me do this. Let me speed it up.
Okay.
Let me speed it up.
Yeah.
I was doing some more.
How high can
I just
t
add a
get?
0 or multiply it by
You're
times.
just going to t equals 10. You could go to infinity, but whatever.
What was that? Why did I do that? Hold on. I'm gonna do.
So each time,
Hold on. I didn't do it.
each time you add a new dot, then the red circle changes. It gets smaller or larger.
Yeah, it's gonna be very obvious in a second. Let me.
Yep.
I was trying to do it, but you know
I know
me
where
and
it's going.
GeoGebra. I'm not.
Yeah,
Not friends with him yet.
It's
GeoGebra.
okay.
All right.
All right. So we made t much larger.
As you notice, that sum and that circle have this relationship that come pretty fast after summing.
Mm-hmm.
Is that the ratio of the radii starts to converge onto a fixed value. And that fixed value for this 0 is 1/2. Mm-hmm. So the individual points, the radial vector of it is exactly 1/2 the radius of the sum. Mm-hmm. And now we're going to.
And before you move, can I just make a couple points? Again, I just want to reemphasize the purple circle is the innermost dot, which eventually is going to reach the center when t equals infinity. And we know that the red circle is the sum of all the dots, and it's half that distance. So it is also going to converge to zero.
Yes, actually, I think I said it backwards. I think so. The sum is 1/2 of the points. Yeah, sorry, I said it backwards. So you see the
so
blue
that's even
spiral.
stronger.
The
It's
blue
even stronger.
spiral. Yeah, the blue spiral is I put a little circle on that on the point that it's doing, and then the eta function is summing from those points. All right.
I just
So
want to say this is a really, really special thing. You're showing them the special case. That red circle converging like that only happens when the Riemann zeta function is a zero. And
yes,
that's what we have in
exactly.
this
In
condition.
all other cases, it's
It
infinite.
never happens any other
It's
time.
only the zeros, yes. And now, and so then we can, now it's a different thing. So let's kind of, all right, sum that up while I'm pulling up something, the next thing, if you could.
Some that
Yeah, just like you were saying, so kind of best you can say.
yeah, I mean, that one blew me away. And I guess it blows you away more when you see, like, if you just move the A, which is the real part, off just a little bit off of a half, or move the imaginary part just a little bit away from the number that we know is a zero, and the red circle becomes large. It diverges instead of converges. And so you're either going to get zero or infinity when you have t going to infinity. And that blew me away. When I first saw that, I thought, oh my gosh, that's a graphical representation. Now what we have to do, Jeff, and maybe you can do this better than I can, is explain why that is the same as showing that the real part of the Riemann zeta function has to be
Yes,
half.
so it's a lot easier to see with some equations.
We're
But
showing
let's,
that the ratio of those two circles, that is the sum of those points of and again, those points are the eta function, all the integer points of the eta function summed together they're gonna tend to zero. When they converge, then that is the same as saying that the Riemann zeta function
yes,
is zero. So
yes.
why is that?
I'll show that in a little bit. First, let's look at just so they can see what you were just saying about how close you have to be to a zero to actually to see that ratio. Here's a zero. I don't know what it is, like maybe the 100th, known zero. Real part 1/2, imaginary part, 211.69, whatever. And the ratio of radii converge pretty rapidly.
Yes.
Multiple decimal points. But let's go here. See, I think I'm.
So just to be clear, this spreadsheet, you actually did the calculations of all the sums of those points.
Yes.
And that's
So I
what you got.
studied it. Yeah, I wanted to study it by.
So we can
I'm
show
like
it
you, I have
graphically,
to
but we
write.
can
I have
also
to.
show it
Yeah.
in a spreadsheet.
Yeah. So a spreadsheet, equations, and everything. So here's the values of the ratios, and this is the graph to the right. You see that's rapid convergence. That's down to 1/2 really quickly. But here's the actual values. As it's kind of going down to, I don't know, 138, it converges quite rapidly to 1/2, fairly rapidly. So it's going. But let me show.
So each of these represents the sum of a certain number of points.
This is the ratio.
Given 1 point, given 2 points, is that what
Yeah. So we have the zeta function.
Yes,
Remember,
okay.
z is that the individual points. Here's the individual points, and then the eta function is the sum of those.
Okay, so the 2.17 represents, that was the ratio given just 1 point.
Yeah, so it's the
Well, I'm
absolute
sorry,
value.
1 would be given just 1 point. 2.17 is given
Here
2
it is.
points.
Here's the equation. It's
Yeah,
it's
I got it.
square.
Okay.
It's the
3 points and 4. So it
the
actually goes
modulus
up a
of
little
those.
bit. It goes up to as far as 10, looks like 10.34. That's the worst it gets, but then it starts coming down again.
Yeah. 10.34 with this particular zero.
It kind of oscillates as it's going down, but it does
But
eventually.
it goes down pretty quick. I mean, before you get
100
to
points.
100, you're kind of it's going somewhere. And we're going to show by the alternating series theorem that of why we will never, when we get out to 1/2, it's never going to go back up again. It's not going to start going off somewhere, so you don't need to worry about this. This is uniform convergence. All right, so we'll show that in a second. But what Greg was talking about before, which is why I pulled this up, if you even move this off that number even a little bit to 21.69, give it a second because it's a big file. Look how far off the ratio goes.
Wow.
That's how fast it is. Because that actually it's clearly going to
Eventually it's going to go to infinity.
infinity. So let's just do
So
200.
you're either going to get 0 or infinity once t goes to zero.
Yeah. So let's look at the graph, then you'll see what's happening.
Just that little bit of change. Wow.
Where am I?
And you could, I don't know.
You can see.
Yeah.
So I'm there's that's how fast it's going off just from 200. It's going to go up to infinity. And when you see the equation, you'll see, oh, well, of course it's going to go to infinity. But it's a very useful property. All right. So that's the ratio. So, and then let's show how close it goes off the real part, 1/2. Let's do
So like
0.499.
Okay.
And we'll watch to see. Give it a second. It's slow. It's pretty darn close with that.
Okay. That didn't
But
change
let's
it,
go
but
look
it's
at
still.
but look at the graph. Wait, oh, you know, you can still see it's going up. It's evident. You see?
So
It's
eventually that's going to
it'll
diverge
go to
as well.
infinity too.
Uh-huh.
Anything off of the 1/2, and you see kind of. Let's get a little close, a little further off.
Well, of course we have rounding error. I mean, you can get an infinite number of digits with these things. So presumably,
No. This is it. You'll see why it goes infinity. It's not. It's not. There's no question. It's very obvious. If a zeta function is 0, and you have 0 in the numerator, and then the other function which you're going to get at the point always goes to 0. If there's a 0 in the denominator, of course it's going to go to infinity. So even if you're slightly off, of course it's going to go to infinity. We'll show the equation in just a second. But this is kind of the visualization of the zeros. Let's go, and I'm going to pull up the paper, and we're going to, so go ahead and summarize that. I'm going to pull up the paper real quick.
okay. Yeah, I mean, the bottom line is we're coming up with a way to show that isn't in and of itself is not a proof, but
No.
it does definitely show you that graphically, which I've never seen anybody do this before, that there's something that's converging, which is related to the Riemann zeta function, and that is the sum of these points and integers of the eta function. When that sum goes to 0, then we're seeing the zeta function also going to 0 at that. And if we go outside of that just even a little bit, apparently the real part or the imaginary part is it's more sensitive to that than it is to the real part changing a little.
So it depends. Yeah, it depends on the value, but yeah,
maybe I wouldn't make a hard and fast rule based on what we just saw, but
yeah. So we're kind of like, but now we have the behavior that we like, that we're going to go and we're going to prove it with that behavior. Okay, and we'll see. So the paper, as you'll see, is identical to all the other drafts, except we removed lemma 2 and 3. So the only lemma left is just, we just call it lemma. All right. So, and that's just, we're constructing the oscillator. So, so that one point, we'll deal with it later. All right. So it's not that important. All right. That point.
Let me just point out, just as a matter of nomenclature, you have zeta sub s of t. It's another way to say it is a function of s and t, whereas the c is just a function of s. Obviously, t is a function of t. The omega is just a function of s. So that's what we could put all those in brackets, but it really gets cumbersome when you do that. So we do it
either way. It's not going to be pretty.
I don't know. And couldn't we
it.
say upsilon of s and put a subscript upsilon? Just
upsilon. So upsilon was a constant. Is a constant. Well,
it's constant with respect to t. Yes, I get it.
But in this case, we're using it as a constant. But we're gonna do something with alpha, which.
But obviously, c is a function of t as well as a function of s, because it would be the point of taking derivatives with respect to t of something that wasn't a function of t.
Right. Okay. All right. So the lemma is the same as lemma 1. We're gonna define upsilon independently of the zeta function. In the proof, though, we're more interested after the lemma. We're interested more in alpha, which is what we use to derive upsilon. And alpha is here, equation 3. So you take this Dirichlet series, and a lot of people say Dirichlet. I'm not doing that because he pronounced it Dirichlet. All right, that's what he wants.
Okay, but we got to respect that.
All right, and so this part's the same, but we're going to come back to the alpha, which is analogy to, I can't say it. Help me.
Analytic.
Analogous to the decay rate of the oscillator. And so we're going to use its behavior to study the zeros. And all it is a simple ratio of the fundamental frequency, or let's just say omega, with respect to upsilon. All right, so alpha divided by omega equals upsilon. That's all it is. So it does make it more, alpha is simpler a little bit to deal, so we went with that.
Can we go back up to go back way up to almost to the top? I just want to clarify. So, oh, there we go. Equation. No. Go back. Go even further up. Almost a little more. There we go. That's it. Okay. What I just want to point out, you just said that upsilon times omega sub s equals alpha of s, right? So we could just put alpha sub s in that equation instead of
we could. And in fact, maybe that's something we might want to do.
Maybe that's a way to do it. But this form is good because it shows that omega is kind of inverse with a derivative of t. So in this sense, this form makes sense. They both make sense. It's meaningful to have both. Anyway, just want to point that out.
All right. You were thinking out loud, I think.
Sorry. Yeah, I am.
No, that's good. That's good.
Just to be clear, Jeff writes the paper. I comment on it. That's pretty much how it works. So I'm commenting as we go.
No,
I have some contribution, but mostly
from the earlier versions, there were pages changed because of your contributions. You just forget about them. All right. He's wishing he did more, but he did a lot. All right. Couldn't do this without Greg or Denny. So just so everyone understands. All right. This is a collaboration, but definitely it is work that I've been working on for a long time. But let's get into the actual proof now of what is really awesome with the ratio of radii. All right. So lemma 1, everyone knows, no one disagrees with that. No mathematician has disagreed with any of the step along the way. So now we're getting into alpha. So this is what's really interesting. Here's the ratio, and it converges to 1/2 for all of the known non-trivial zeros. All right. So we're at this point not speculating anything, but the theorem is that is going to 1/2 because that's going to imply that, and we'll prove that the zeta function equals 0 if and only if real part equals 1/2.
And I just want to point out
really quick. Yeah, go ahead.
When I just want to point out, this isn't the same as that graph that we just did, but it's very, very closely related because we have the sum of things over integers.
This is the same.
Kind of like those points.
This is the same.
Well, that part is the same.
This equation is the two.
So
the two
basically,
circles.
the sum of something over the most recent something equals 1/2. That's what we're proving.
Yes. And that's actually is required for the zeros, and we'll see.
So that's what we're showing graphically, is this equation.
Yes, right here. All right, but we're actually, how it's proven is, it's just really, really neat of how it's proven. It's very, very easy to prove at this point. All right, so here in the paper, we're just talking about those points. That's the z sub t of s. So this is a very, very, very simple function, and it does converge uniformly. As you see in 22, the absolute value is simply t to the minus real part. The imaginary part is completely irrelevant when you take the absolute value. It's all dependent on the real part. Yes. So that of this point itself. So that very easily, as you see as t increases, is going to go to 0 for all s.
Right. And also so the imaginary part of t is irrelevant too, as long as because
t real part of t? T is a real.
No, it's only the imaginary part is going to, when you take the norm of it, it becomes irrelevant. So we're only interested in the real part.
Yes. So this is, so we're talking about basically the uniform convergence is that was the issue that originally, was brought up. And so we got to make sure that's included. All right. Now, so this is what I was saying is we do know that.
This is what the graph is showing is this.
Oh, that's right. That's right. It wasn't shown alpha. I'm sorry. Yes, there's. All right. So we're using alpha.
So they're not exactly the same. They're related, but they're not the same.
Exactly. All right. So all right. Here. Yeah. I'm so sorry. You're right. So
okay.
This right here, 23, is what we're seeing, but we're using alpha, a form of alpha, which is makes it useful for the proof. Okay. Right. So you have to use alpha for the proof. Just having that thing, the ratio appearing at 1/2 proves nothing. You have to use alpha or upsilon. All right, so we're going to use alpha. And so now we're not actually determining anything. Remember the whole thing, we're set 0, zeta function equal to 0, and we run into problems. Well, we're going to evaluate it. We're going to look at it, but we're not going to say anything about it. Okay, we're allowed to do that. 24. All right, so 24, if zeta function equals 0, this is what alpha is going to look like. So we want to factor that out of the infinite series of alpha, which was above. I'm not going to go back to it. Then we get that part here is what remains of alpha after the zeta function goes to 0. What's interesting about that, and it was in all the previous drafts of the paper for the Upsilon, is that equals 0 if and only if real part equals 1/2. That remaining factor. It's this part over to the right side of the minus sign, the second term, is what's most interesting, and that's where we have the ratio of the radii is going to be impacting. Okay, so the eta function here, this is the relationship with that to the zeta function in this equation. So to look at 25, so we have in the first equality, we have the infinite series of the eta function or the minus eta function. And this is what it looks like if we express it in terms of the zeta function. All right, make sense? Now we're going to evaluate this first term just because we took it out of it's kind of from the previous drafts, but we're doing it in terms of alpha now. That we're showing that this implies real part 1/2 if and only if. Very simple, 26, okay? And that's simply because 2 times the imaginary part of s plus I times I will never equal 0. All right, so it only equals 0 if real part equals 1/2. All right, now we're going to evaluate the modulus of this, 27. Now 27 is the same as that sum of alpha, but it's the individual points, all right? Now, when we already talked about this a lot with the graph, so the n is a natural number, and then we get 28. Let's go here. Let's just get to 29. This is the important stuff. When you look at this expression, we're just going to call it r sub m and n, r. So we have this, we can then take the same thing. What we notice is the first term in the numerator and the first term in the denominator are the same, of course, because the ones in the denominator are simply the points, and the one in the numerator are the sum of the points. Since this is constant, we can just call this k, okay? And we can solve for k.
The whole thing is k, or just
the first
just
term
that
in the numerator and the first term in the
okay.
denominator, 29.
Okay, we're going to call that
Make sense? We're just going to call it k.
No, I do. I just want to be, I want to go slow so we don't lose people.
Good. No, you be there to slow me down. All right. We're going to solve for k. Important thing, and this is what I was saying when we were talking, we had a meeting last week about this, is we can't set anything to 0 until we're done, because we don't want any of the problems that we've had with the last proof and people. So we're not setting anything to 0, and we're going to use partial sums. Okay, so not even the zeta function can go to 0 at any step in this process until the very end.
And can I point out the partial sums idea is we can't get an infinite number of points, but what we can do is get a finite number and show that finite number is going to converge, and then we don't need an infinite number. That's
well, at the very end, we're going to let it go to infinity.
Yeah, we let it go to infinity, but I'm just saying we get
During
a
the
partial sum,
manipulation.
we let the partial sum go to infinity. That's the same idea as adding all these points together and seeing that that's going to 0.
Yes, yes. But the manipulation in the steps, we don't want any question that we're dividing by 0 any step of the way. So nothing is going to go to infinity. Everything is finite every step of this manipulation. All right, so we're taking this ratio. We're going to solve for what conditions makes this 1/2. Why does it go to 1/2 for those known non-trivial zeros? First, solve for k. You get 2 solutions, it's absolute value, but only one of them is relevant because the solution is for the ratio is less than 0. All right, so that, and the real part of s is less than 0, which the infinite series wouldn't converge anyway. So we're not interested. We're only interested in the critical strip. So we're only going to use the first solution when the ratio is a positive real number and the real part. I think this is wrong. Oh yeah, here it is. Real part of s is greater or equal to 0. All right, so we're only interested in the top solution. So we did this in step. We just did it for k, just so we can get rid of all. So
solution, would that give us the trivial zeros? I'm just curious. Hadn't thought about
No,
that.
you can't because eta function doesn't converge in the
Gotcha. Okay, we
when
need
the
a
real part
different
is less than
mechanism,
0.
but that's been done before. So okay.
Yeah, exactly. We're not interested in trivial zeros. We're using the infinite series now, just again because we don't want anyone question anything. So we don't want to say, well, you're not using any properties of the z function. Well, in this we are. All right. So in the past we weren't, and in this point we are. We're just using the infinite series. That's all we need, and we're using the eta function because it converges in the critical strip.
I'm
Yes,
just throwing this out, and I don't mean to take you too much of a tangent, but it
no,
would be
it's fine.
nice to be able to show the trivial zeros in a graphic way as well. Just set that aside.
Well, you can show what you're working on, and you
Yeah,
can
I'll
go
be.
there.
Yeah,
All right.
that's just one more thing to put on my plate.
And then I'm going to give that promissory note of the $1,000.
Yeah,
It's
yeah.
very
Well,
important.
I won't hold you to that.
And I'm going to give it to.
I know you want it. I know you.
What's
want
that?
it.
I
I won't
no.
hold you to that. I know you want it. We're going to.
I
come
want
up.
them to do something. I want people to do something, and it's very good and it's very useful. All right.
Here's what I think. What I'm hoping. Here's what the projection. We put together a good video. Is well produced that makes the whole thing clear and graphically, and then maybe we get some people like I'm just put it out there like what's his name, Gerhard from not well
Mm-hmm.
what is that, Mathologer, or
Mathologer.
there's a bunch of other people, three blue, one black, three brown, one blue, you know what I mean, that guy and a couple of other guys who have well-known mathematical channels. They can do probably a much better job of making this graphical thing than we can.
Yes.
And then if they can put it out, and they obviously have a much bigger audience too. That's what I'm hoping. I'm just putting that out there. Or if anybody listening to this is able to do, make mathematical videos, we are very interested in speaking with you. So I'll put that
Good.
out.
Yeah. So let's show the proof. This is so easy.
go
All
ahead.
right. So once we have this ratio in terms of we get solved for k, that we're just doing this to get rid of the second solution so we don't have two solutions going all the way through this. We're only dealing with one solution. Only one is relevant. All right. And then once we solve for k, we have the explicit form of k. Remember we said the term is k. So we're just going to put that on the opposite side of 32. And we're going to solve for z sub s of n. All right. Now remember, this only goes to 0 for all s's. It goes to 0 always. It has to be equal to 0, right?
Can I back you up a step again, Jeff?
Yeah.
Where did we define n? Can you go back up, please?
And enter the natural numbers, the natural t.
Okay, that's when we did the sum. So we defined, where did it first get defined? Was it right here?
Somewhere
When we
right here.
defined alpha sub s. It's in
Yeah.
Okay. Okay. And then
Z
things
sub
became
s of n
functions
is the
of
point
n.
at any
Okay.
natural n, the individual terms of
Yeah,
the
yeah,
infinite series of 25
Okay.
over there. All right.
Just didn't want to brush past that. Okay.
No, please. All right. So now we have this. We now have the means to solve for z sub s of n, which must always equal 0, but it's not here because we're using the partial sums only. Now we can let it go to 0. There's the algebraic expression. It goes to 0. You have two possibilities. It can be 1, or it could be a real part of s equals 1/2. But if we can go rule out 1, it's very easy. Is we return to this step over here, 29, put a 1 here, let r equal 1, and then solve back for it. And what we get is it reduced to only one solution. Everything drops out to being real part 1/2. All right. So but here, sorry, now it's down here.
That's the final proof. That's the end of it.
It's the end of it. All right. So that's it. All we do is we solve for z sub s of n, let it go to 0,
Mm-hmm.
and it's going to give us the only possible time that's ever going to, that's for when it's equal 1/2. It's saying it's only have two solutions, 1 or 1/2. Mm-hmm. It's always going to be 1/2, but we have to show, and then why? Well, you can look to see why if you separate it. Let's see the first factor. Let's see can you see my cursor? Are you sure you can see my cursor?
Yes, I see.
Okay,
your cursor.
good. So this factor here can be expressed in this way. This implies 1/2. This factor over here can be reduced to 1. All right. Mm-hmm. But we have to find out, well, why would that ratio go to 1? Well, go back and throw it to 1, let 1 be in there, and solve back for when it is 1. It ends up saying the only possibility is when real part of s equals 1/2. Either way, it says they're critical zeros. So let's go there. So what we do is the limit of the ratio is always 1/2. Always 1/2. So now we return to the ratio before. It says no matter what, whenever zeta function is 0, that ratio between the sum and the points is always going to be 1/2, no matter what. Therefore, go to 29 and set that to 1/2. And then what does that say? Now, what is the solution that allows for both the points to go to 0 and the zeta function to go to 0? And it happens only when the real part equals 1/2. 37 and 39. It's very, very simple. So now, what would happen if you go and set 29 and set r equal to be like 1/3? Or no, the real part of s equals 1/3. Let's just say we can lie, and I've done this, and say, well, we're going to do that anyway. And let's say the real part equals 1/2 of s. So say there's a 0 in that area. You go back and you solve for z here, and it's going to give you a complex number. But we already know that z always has to equal 0. If you go to any other value other than 1/2, it's going to say z is a complex number. But z is always a 0. Why? Because it is so very, very simple. Where is it? That has to do with the points of the eta function. Where's my thing? Right here, 19. That is 20. The limit is always 0 for all real part of s.
That's basically saying the spiral is going to eventually come to the middle.
That's all it says. So you let that real part equal anything other than 1/2, and then set the zeta function equal to 0. It's going to give you a complex number. It's got to do something, but it's not. The only solution. You get two possibilities is 1 and 1/2. But if you go then and plug r equal the ratio as being 1, you know that the sum is going to be that
it's basically s minus 1 plus or minus the conjugate. And
it's super
plus,
simple.
The plus doesn't happen. And by the way, can you go up, please? To
I can go wherever you want.
Just go up another page or so. I'll tell you when to keep going. Okay, there. No, that's at 24. 24, please.
Yeah.
Here we go. The definition of alpha sub s. I just want to point out
that's not the definition.
Okay, but that's a nice equation. You're right. That's not definition, but it's a nice equation of alpha sub s. And you notice it has s minus 1. It has an s minus 1 term and an s bar term, which is the conjugate term. When those terms are equal, okay, that's when real part must be 1/2, because s plus s bar is going to be twice the real part of s.
Look at 26. It breaks
when
it down.
When that equals 1, 26. Then the real part is 1/2. That's just
26
another way of
breaks
saying
it
the
down.
same thing. And
exactly.
We keep seeing those same terms over and over again. So that's what
they're geometric. They're a geometric relationship.
Yeah,
it's in that point 0 to b.
That's where you're getting it from. Is that one of those?
Oh, you're breaking up. Are we losing you?
No,
okay, we lost you. All right, so that's okay. All right, go ahead. What were you saying?
You can't hear me?
You can now.
Oh, okay.
You froze.
Oh, that's interesting.
It's not your fault. It's my internet is unstable.
No, I know. Well, I mean, it might be my fault, but anyway, I just want to say that those terms s minus 1 and s bar, those terms are constantly showing up in all these kinds of derivations. And I mean, we've been dealing with those terms forever, and they show up in the diagrams as well.
Let's go to where that is. Yeah. Let's see. Give me a second. Go ahead and talk about that a little bit, because I gotta go find it.
Well, I just wanted to say, like, if you which I'll show later, you take s minus 1. Well, that's like moving it to the left a little by 1 unit, and then you take the complex conjugate of that. That's like moving it across the real plane. Okay, well then when you're going to make some statement about those two things, if those two things are going to be equal or on the same line, which is kind of like what you were showing earlier, those two different lines, the only way that happens is when the real part of s is 1/2.
Yes.
So that's just sort of that isn't proving it, but ultimately the proof does come down to just that very thing. And so we have to get to the point where that is the proof, but that's the last step of the proof, showing that those two things can only only happen when the real part is 1/2.
Yeah. So that comes from this part. So this is the geometric aspect. It's this line here from 0, the length u. This is where it comes from.
This is the old paper.
Yeah, this is
really old.
The old one.
or the
Well,
long,
it's still up there. It's long form. It's still up there.
the long version, you know.
So if you break
I
that
think we need
down,
to update the long version too, to be honest.
exactly, exactly. But
But
I'm gonna leave the research in there.
because
It's just gonna be. I'm
you
gonna
have
take out
things
lemma
like
too.
arg of s, and I would call that theta, but that's just for whatever that's worth. Arg, it's an angle, but
Okay.
anyway,
All right. Well, so any
we won't
case,
get
this.
bogged down.
All right. So what we're looking at is this length here geometrically is this equality where the absolute value of the cotangent of 1/2 theta argument of s minus tangent 1/2 argument of s equals the inverse 1 over imaginary part of s. That only happens when real part of s equals 1/2. And the reason why is because of this: the cotangent minus the tangent minus 1 over imaginary part equals the complex conjugate of s plus s minus 1, which is that issue. That's the one that goes to 0. Yeah, so that's where that comes from.
Can you move up to the diagram for 1 second? I
Yeah.
just want to show you that. Okay, you see where arg s is, that you haven't identified. Arg s is the angle between the horizontal line and the line that goes through s. So that
over here,
the half tangent, arg s over 2 is that half angle. That's all I'm trying to say. Just pointing that out. Maybe that's obvious.
What did I do?
No, you didn't do anything. I just want to point out, you know this. I know you know this. I'm just pointing out in case people missed it, that the argument of S is the angle between the horizontal line and the line that passes through S. And then half that angle is the one that goes, if we draw a circle through S and then draw a line, that's the half angle, which is hopefully everyone would know that the angle connecting to the circle going through the center, that is always half the one that goes through the center, the angle that forms with the center itself. Basic thing in geometry. Anyway, so when you're talking about arg s over 2 down in those equations, you're talking about that angle. That's all I want to say.
Yes, because that's the complex argument. That's why I call it arg s.
I get it.
All right, so that's why that condition.
I just want to clarify.
Yeah, so that's why that condition happens. And here's, let me go to where it says, because, yes, right here, this is where we made our error. So U is not defined as this, but this, such that this. This definition, what makes it possible to continue with the proof. But
I wouldn't call it an error.
Whoa.
I would call it a.
Hold. Do not interrupt this. This is the most important part of the whole video.
Okay, go ahead.
But it's not defined. It's already, you can derive it. Therefore, the proof is implied simply from S. That's the thing. It was an error. It was not defined at all. It doesn't need to be defined. So when you define something that's already defined, then we run into a problem, which is what the problem was in the paper, which I want to show. It's is very important. And then you were agreeing with me, but it was kind of interrupting my thing. Right, hold on.
I'm sorry, I didn't mean to do that.
No, that's okay. Okay, hold on.
It was a surprise to you that you said when you put up your graph, everything comes from S and T. It's like you don't need anything else. Those are the only inputs.
S and T and everything. Yeah, everything.
You don't need to define anything else. Everything else falls from just those two quantities.
And when you do try to define something along the way, you run into errors, which is what we got. So here's the issue right here. This is kind of like the last paper. So in this theorem, all right, it's very simple. All right, we're saying there's no solutions. It's very similar to our real part plus real part equals 1.
This is your analogy.
Yeah, it's an analogy. So go ahead and what's the proof? How we prove this has no rational solutions? Well, we simply factor out the 1/2, divide both sides by, or multiply both sides by 2, and we have x plus y equals 2. So therefore, there's no rational solutions. All right, well, but what if we already proved this value on the right-hand side, this equality? If we've already proven this, that it equals 0, then we're going ahead and we can't make any assumptions that it's not. We already proved it. And so that's the issue we have when we get into ours, which is what we had here, is real part of rho, remember this from the earlier drafts, plus, its partner on the other side of the imaginary line equals 1, has no real solution. It's identical problem. But we already proved that the real part equals 1/2 earlier. So I went back and I go, where did we do it? And it was in that definition. Is we defined something that was already proven. It was already implied that cotangent is equal to or 1/2 cotangent is equal to.
Yeah.
With
So
that,
the new version is actually simpler than the old version.
yes, we just removed two lemmas that we already proved something as soon as we created or actually you have this interesting philosophy. You said actually it comes from your son. Is nobody invents anything mathematical.
Right.
We discover
discover
it.
Yeah.
In this case, I am completely convinced because it was
It was there all along.
I thought we defined something that made the oscillator possible, but in the end, it was geometrically implied already, and we just kind of put the puzzle pieces together, and that's what it is. So the proof is easily implied, and that is what you're working on. Do you have your
Kind of.
GeoGebra thing?
I would like to, but I'd like to do a couple things first.
Please.
If you can return to the paper, I just want to point out this is something that I played with quite a bit. If you could bring the paper back up, the idea
Do
that
you want the original, the longer version, or the current version?
I just want the first equation. I just want to point some things out about the first equation. The derivative with respect to t in engineering, sometimes you can think of that as sort of like an omega, right? It's another time. If t is time, omega is 1/time. So let's call the derivative with respect to t omega t, just for fun. Go to the paper if you don't mind.
Go on.
Then what you could do is because you have this other omega naught in there, we could just switch the roles of omega t and omega naught and go way up to the very top, the very first equation.
I see what you're saying, and you're absolutely right. Yes, I know what you're saying.
Okay, and this is just a funky thing. No, not this bar. Go down. There you go. Nope, down one more. Well, no, that'll work.
Two, I think, is when.
Yeah, that'll work.
Yeah.
I'm sorry for changing. Okay, all I'm trying to say is you see omega sub s. I called it omega naught. That was wrong. So think of d derivative with respect to t as omega t. Let's call it. So then we have zeta sub t is equal to omega t squared c sub s times upsilon of s omega t plus omega t squared c sub s. Okay, and then all we would have to do is just take everything over to the other side, or divide everything through by omega s and omega t, and then we could have a second order differential equation where the zeta function becomes the middle term, the coefficient of the middle term, which is the damping coefficient. So instead of upsilon being the damping coefficient, the zeta of s term becomes the damping coefficient. You can just reverse everything, and everything is completely analogous.
Yeah,
that's all. To me, that's amazing. So what I guess I'm trying to get at is the alpha term. Well, no, the upsilon term is completely analogous to zeta function itself. It has a lot of properties in common with the zeta function itself. Just from an intuitive point of view, you should be able to.
It is. That. In fact, if you look at it, you see it's very close to like a Dirichlet alpha or like an alpha function, except for the only difference is that it's not analytic. So in certain regions, because of that complex conjugate, but alpha is. So alpha, because we
it's this whole business of going to zero that makes having an alpha function as well as an upsilon function useful to have both. Because
in fact, because with the zeta function, we couldn't just showing the ratios. You can't prove anything with it,
right?
At least as far as I can see. But with alpha or upsilon, it's very easy. The ratios because it's that first term and the numerator denominator is constant for all t. Good. So this is.
Go ahead. Sorry. Could you go back to the diagram? I want to show a couple things on your diagram before I show you my stuff.
The GeoGebra? Yeah, sure.
Please. Yeah. Yours is more complete than mine is. Mine is maybe, I'm trying to make it simpler. So go back to get a small value of B so we can see everything. Okay. And then expand it out a little bit. Perfect. All right. I just want to point out the important point here is the point E. That's a really critical point. Once you have E, then of course you have the radius of that circle that E lies on. You can calculate the point A and D from that. You can calculate the point C, which is just directly below E. You can calculate the point B and then J just from the -1 up to that line. And that gives you whatever that point is, T, the brown circle from that. And of course, the purple circle is just the unit circle.
Right.
Okay, so once I can calculate the unit circle, once I get point E, I can get everything else except point F. I have to calculate point F a little differently as well. So bottom line is what I do is I construct the points E and the points F strictly with geometry. So there's a complicated formula that Jeff uses to get the point E, and it has tangents and it has whatever logarithms. I can't even remember exactly how you derive point E.
Right here.
But yeah, there it is. And you did it parametrically, and it's based on all those things. So I said,
Not
yeah,
that
I should be able
complicated.
to just be able to do that graphically, just using uh, you know, just using circles and straight lines. And so that's what I did. And then I can also calculate everything just using circles and straight lines, which is the way the Greeks kind of used to do things. So that being said, I can move to what I'm doing, which is I haven't gotten as far along as
That's
you have
okay.
yet.
I'll introduce it while you're
Show you
getting
what I
ready.
have.
I'll introduce it when
So
you get ready.
should I do share screen now?
In a second, let me show one last thing in here, but you can find it. But I did want to note a very important detail that a lot is often missed. It's very important is that this radius is 1 divided by the imaginary part of S always, and that connects back to the unit circle from this unit line JL, which is very interesting. That's how you get this this nice
Yeah. So I don't know which is
synchronicity and timing. So these
if
two
you have
points.
L, you can get J and there you can get E, or if you have E, you can get J and you can get L. Either way.
Yeah.
But the way you constructed it was we got E first, E and F, and then everything else just falls out. So
Yeah, he was
that's kind
pretty
of how I
quickly. Yeah,
approached it.
pretty much. Yeah, from the very beginning.
So anyway, all
All
right.
right.
Are you
Well, go
ready for me
ahead
to?
and share yours now while you're getting ready. So Greg, said I want to do this with the compass and ruler, and I'm like, well, computers have come a long way. But the neat thing about this is you can show this way how everything is implied from one to the next, one step to the next, and just from knowing S, you can get everything to calculate all the way, find geometrically why the zeros of the zeta function happen and what conditions they do not happen. Just from S alone, it's NT, sorry, NT.
T, right. Can you
Or
see my screen?
Yeah, now it's sharing, so I see it. Go
Okay,
ahead. Go
good.
ahead and
All right.
show
So
what you
as you
got.
can see, S is just a complex number. And now I did it differently. You did A and B as the real and imaginary parts. I just thought I'd just do S as one
Just drag
thing.
it around.
So you can drag it around.
But you can't drag it all the way to the left. You can't drag it past the imaginary line, or it won't converge.
Well, I can do anything, but
Well,
I'm
when
not
you put
limited.
you don't have the eta function in yet, summing. When you
Well,
sum that, it's
at
not
this
gonna.
point, all I have is the unit circle and my point S. That's
Okay,
all I
it's
have.
very nice.
And so and just to be clear on the unit circle, there's a few points that Jeff identified in his diagram. Just so you know, and I've said this to you before, but the way I understand something is to do it myself. That's just
Right.
that's how my brain works. So, I noticed that your point K was just on the unit circle. The point P was just on the unit circle. I'm going to make use of the point I2, which is just the point 1, 1. So
Okay.
those points don't change. So I just have a little checkbox here to mark those points on the unit circle. All right. And then I want all the points related to the point S, as S moves, are just the imaginary part and the real part. You call them A and B. I think of them as S imaginary and S real. So I named them
It looks
different.
nice. Yeah, that's good.
But that's basically all that does. Now, the important one was how do I get that point E given S? So sometimes S is greater than E, sometimes S is smaller than E, but it's always on the same line. No matter where S is, E is going to be on that same line as S. So here's how I did it. Again, we already saw that. Whoops, I didn't mean to do that. We saw that complicated form. I wanted to just do it using lines and circles. So I start with drawing the blue circle, which passes through the x-axis at the point A. I called it A prime because we use A for something else in your diagram. So I call it A prime. So that's all I do to get A. Then I take the distance from A to I prime. And again, I call it I prime because I is used for something else. And then that I can basically take that and create a new point. Excuse me. I'm sorry, from A to S sub R, from the point A to the real part, that part then becomes that distance becomes the center of the circle at I prime. And that gives me the point B prime. Does that make sense?
That's cool.
Okay. So then I have that first dotted, that's the B circle. Now that I use that point I2, what I do is I split I1 and B prime, and I draw that dotted line, and that gives me the point C prime. Then I take the point C prime, and let's see, what do I do next? Doodly-doo. Trying to remember, it's been, oh yeah, I just draw that circle that passes through B prime and I2, and I get the point D, which happens to be the same as the D in your diagram. So from D, then I draw a circle and I get the point E. So I have D and E just as you have it in your diagram. So I can now get rid of, I don't need those other points. I now just have all the things that are related to E, and it's a lot cleaner. Remember I said once I have E, I've got everything else.
Yep.
I've got all these other points that are in your diagram, and the point, and I use the same labels as you did. So there's the point A, the point D, the point E, and I think it's pretty obvious how I can do that graphically. So it's just a few steps to get that point E just using circle and compass. Anyway, then I did, once I have E, then I want to create a curve. Let me do that curve first. So this is the curve based on T, and I lost my T here. I don't know where it went. I have somewhere, I lost it. Oh, there it is. Okay, I'm sorry. Okay, so I just, like you do, I move the point T around. Now, I did it a little differently than you did it. The point you were trying to prove was that the derivative was, you wanted to know that the derivative was equal to this angle. So I calculated the angle, and then I calculated the derivative, which is basically how much is Z changing. And then I have Z sub D hat, which is how much it's
Can
changing.
you zoom in a little bit? It's hard to see for me.
Yeah, I can zoom in. Sorry about that.
That's all right.
Okay, so Z is the same as before, and you were interested in this angle. You were trying to prove that that's equal to the angle between that and the derivative. And so I had to take the derivative, which turns out to be, I could get that geometrically as well. But because sometimes the derivative was really large or really small, I wanted to normalize it. So all this is Z of derivative hat. It's just normalized to 1. So that's all that is. Then I just scoot it over and I get the point ZA, and I calculate that angle. And that is, in fact, the angle between the curve and the that going out there, which turns out to also be the angle between the derivative and that. So
Nice.
That's what you were after when you asked me to first take a look at this.
Yes, that was very confusing for me.
So yeah, hopefully and you'll notice that angle gets closer and closer to 90 degrees as we move in, which you would expect. Once it gets to all the way in, it's 100%, where it is. But where it started, that is a function of S. So let me move out to, let me play with S here a little bit. So you'll notice that angle changes. The beta sub Z changes. It's also a function of S. Okay, so it's a function of T.
That's what I think is the most beautiful thing of the whole diagram, is that angle right there and how it.
Yeah.
For me too.
And that, anyway, that I can play with T.
Yeah, the angles and everything.
Now, what I haven't done yet, and
the zeros.
what I need to do, and I just got to find some time, is put those points in like you did when they add them up and things like that. What I have is these check boxes at the bottom, so that if it gets too busy, like for example, I'm not interested in all that triangle stuff at this point. I just want to see this curve. I can turn that on or off, and that makes this a little easier to see. So I did that as well. All right, and then the other thing that I did was I calculated the point F. So basically, I take the point S and I subtract 1, and I got F prime from that. And then I find same kind of idea. I find let's see. Then I find the reflection of that. That gives me F double prime, because you have to flip it over the imaginary axis to get F prime. And then I find the circle that passes through the origin. Oh, hang on. That's not what I did. How did I get? Oh yeah. Okay. First, then what I did was I find the point. I'm sorry. It's been a while since I've done this. I did this line for, oh, that's it. Now I remember. Okay. In order to reflect F to F, F double prime to F, I had to get this point that passes through I want the point that passes through the origin that's perpendicular to this line, and that gives me the point G prime. That's what I did. I forgot what I did.
That's
Then
okay.
I find the circle that passes through F double prime and G double prime, and I find, and to do that, I get this green dotted line here to give me the point H prime, which is the center, and then I draw a circle around that to get the point F, and that's how I graphically can get the point F. So once I have it, then I don't need it anymore.
And that's a very important part of the oscillator too. That's the
Yep.
those are the derivatives. Once you have that, you can get the other derivatives. Yeah.
Your diagram, you can show this algebraically, that only when the real part of S is a half does the blue line and the green line line up exactly.
And that's what leads to the zero.
Yeah, you're right.
That trajectory.
It's real easy to show algebraically, and it's clear geometrically that's true, just from this.
Yeah.
As well. So anyway, now that we have the point F, I can create this curve that starts at the point F, which is you have. Now, I don't think that this is not a curve that you used, so this may or may not be useful.
I don't use the tangent.
Based on the same T, this curve, the angle is not dependent on T. It's just a straight logarithmic curve. But anyway, we may not use that. But anyway, that's the parts I have so far. What I want to do next is add up the points like you were doing.
You don't have the Z curve in yet? The points?
No, I did Z curve. I already showed you that.
Oh, okay. Yeah, all right. You're right.
I already showed you. So basically, that's all I got. And what I want to do is make this prettier, and I want to show it all the various curves. Like the Riemann zeta function. We should be able to, we can do the eta function. Well, I don't know. I'm thinking we can show a lot more than what I'm showing, and I have envisioned quite a bit more than what I'm doing already. But this is a start.
It's very good. It's very good. All right, go ahead and stop sharing. I'm pull up the last image, and then I'm going to kind of show what I was going to do. All right.
If of the $1,000, maybe that's $50 worth. So.
I like it. All right. So in the paper, this is what we have. This is the $1,000 thing, and let's say I don't know. Of course, please understand, it's only if the mathematics community accepts this and we get the money from it. But it's a very, very good step in making that happen. If more people do this, and I'll offer up the first 5 that do this. Okay, so $5,000. All right.
We're talking about people who make math videos.
Who do this? Well, no, that's your request that you can offer.
Yeah.
This is my request right here. We have right here, and I put this in the paper. Once you have the oscillator. There are a number of ways to show that it is already proven. A number of ways. And it really took me, I don't know.
25 years?
Once I had the oscillator, it was like, we thought we had a proof the other way, and now I realized the error in that. But this, like I said,
we did. We just assumed that we didn't. It's kind of really what you were saying.
Yeah, we did. Well, what we were trying to prove that we already proved, and we failed that. So Lemma 3 and all that stuff was all pointless.
Unnecessary.
This is what you need. This is all you need right here.
I'll take the blame for that.
No, well, we all missed
part of it.
We all missed it, and but here's the issue right here. We think that it's important that people start learning the oscillator and this geometry here. So since there are a number of ways to prove it, the best, or the one that I have, presented, and we're going on, Greg's doing a different way. He's working on a geometric proof. I'm going to offer $1,000 for anyone who could just go ahead and find more ways of showing that it's already proven. More ways of showing that it's already proven based on what's given. For each time, where's my thing? For each time you find one, and this could be one person finds all 5. There's many, all right? That's fine. This is one way to do it, to show it, is just looking at the ratio of the radii. That's one way. It's not the only way. With this diagram, you can find, when I said, hey, I'm going to go look into this deeper, it was about a week I came back with this, so it's not long. So you're talking about with the information there, obviously you're going to have to understand it, as much as we do. Oh, we're not on a 0. That's why it's not converging. I was waiting for it to converge. It's not converging. Not on a 0. Now I am. This, like I said, this didn't take long for me in a week. So I don't
Hmm.
know. I mean, a week is kind of $1,000 a week is not a lot, but I can't pay it until it's it's success. But if you could find other ways to show that the
Hmm.
proof is already demonstrated, just showing the proof in
Hmm.
different ways. All right,
Hmm.
I got this way with the ratio of the radii, but there are a
Hmm.
number of ways using this diagram. What I'm going to do, and you can publish it too. That's the other thing. Put up a paper up on thing. I'm going to make it with Greg and Danielle. We're going to
Yeah.
go
Well,
over
I
a
said
little.
this a long time ago that
Yeah,
that this whole oscillator idea, we've known it for years, that it is just rich with a lot of ideas. And
yeah.
it's amazing that it's taken us this long to get this far, but this is pretty cool. And I believe that there are just tons of different ways, tons of different directions we haven't even thought of that you could go with
Hmm.
this, that would relate to this in some way. Anyway,
Yeah, because there was some mathematician, he wanted to reference the paper, and I said not at this time. We're in
there's nothing
preprint.
to reference. So you can
Yeah,
reference the preprint, but yeah.
well, yeah, we even kind of have that eliminated so no one can reference it, at all because we don't. We can adjust the license though. We'll get it in that way, and that way you can reference it and you can write it. If you think there's an error, go ahead and publish paper on it that there's an error. There's no error. This one is
There's
straightforward.
not much left.
Yeah,
There's
this
nothing to.
this is pretty straightforward. I mean,
Hmm.
it's if you look at those last equations of the paper, there's a number of ways to do it. $1,000 for each way, up to 5,000. Five people or one person with five different ways to show how the proof is already proven. Different ways, can't be the ratio of the radii. All right, I did that one. All right, so five
Something
different
to.
ways, and to show that the proof is already there. You got to read the paper to understand the lemma and the construction
Mhm.
of the oscillator, and then I'm going to make this available.
Yeah,
Share
that's the
it.
other thing. And I wanted to say we use GeoGebra. There are other tools we could use like Mathematica and stuff, but
Uh,
GeoGebra is nice because we can put it up and anybody can access it. It's free.
hmm. Now, how does that work with editing? Do I have to, can I put up an
Uh,
editable
you
version and then
you
they copy and save it
you can
somewhere
yeah, you
else?
can we can upload both.
Show me how to
Both
do
are
that. Okay, we'll get.
well, not right now, but I will.
No, I got things that I do.
It's possible to have both.
Yeah, but we want to have it so that you can go in there. I want everyone to be able to go in, and I
Play with
think
it.
you can see the equations, right?
Yep.
So, yeah, can they see the whole? I can because I'm editing, but I want them to be able
No,
to see the
I can see
equations.
it. It's there.
All right, so
Uh,
this, yeah.
yeah, if you can get into an editable version, you should be able to see all the
All
equations.
right, that's what I'm gonna do. That's what I'm gonna do. All right, so
Total
in the
transparency. We
comments,
want people to help.
if you're curious about this, ask me how to do it. What I'm gonna do is I'm gonna share this, and you can get information. Also, the paper, we'll set it so that you can reference it, even that you can publish a preprint. Of course, you can publish it. But also journals too. I'm gonna put this out there. If you're not a reputable journal, don't email us. We're just gonna throw it away, okay? It doesn't take long to find out. And I'm not saying that there's anything wrong with new. I'm not saying there's anything wrong with new journals coming out. Like this one was only it's fairly new. That would be awesome. But it has to be that that it's not only targeting people who are pariahs and
Well,
outside. It
let's
has to
be
be.
honest, in order for this paper to get accepted by mainstream academia, we
Yeah.
have to have a somewhat reputable paper
It
that's
has
going
to
to
be.
publish
It
it.
has to be without
And
question. Otherwise, we'll just leave it on ResearchGate, which is fine
yep,
with me. I don't. Perlman didn't
it's
even
just as
publish it.
well
He
so
had it
far
just up
because
on archive.
we
Yeah.
we were able to make this update, and I think the paper is better than ever. And we wouldn't have been able, if we'd published it before, it wouldn't have been as good. So
No, no, no. Once it's published, and if they would have missed it, think of the nightmare.
yeah, we wouldn't
And
want to cause nightmares.
no, we want to have a
It's
real proof.
strong
We're
now.
interested in the truth of this. That's what I said when I saw that. I'm like, well, let's back up. Where did we make the error? And I go, as soon as I set in zeta function equal to zero, and manipulate anything after that, that's the problem. And that's when everyone can jump in and add any function they want that has zeros off the critical line. But this is the oscillator, as you see. I like things that work or don't work. There is nothing wrong with this oscillator. It is working, and it alone shows the zeros and what makes them unique and why. And it always has to do with the real part 1/2. So, like I said, if you can find other ways to show that, I'd love to see it. Leave in the comments if you have any questions about that. But yeah, $1,000, five different ways. Just one is $1,000. You know, up to
$1,000 a pop.
$5,000.
No, I got to get busy. Jeez.
Yeah. So if Greg gets them all, then well, if we were to
You don't
get
need to pay me, but,
if we were to win that prize, you would already get some anyway for that. So you wouldn't need
Very
the
good.
$5,000.
Yeah,
That's all. So that is
again,
it right there.
I'll just point out again, if you or you know somebody who has a math channel who does things like this, we would love to talk with you and see, you know, we'd like to find new ways to express these ideas. And,
Yes.
you know, the more clarity, the better. You know, that's what we're looking for.
Yeah, no, this is a lot of research for people they can use. There's a lot of tools in here, and it'll benefit mathematicians. If it's ignored or not understood, it's going to help. It's not going to help anyone. But this is the big thing about it. The zeta function or the Riemann hypothesis is one small part of this. So this is opening up a lot of different avenues, especially when it comes to physics, like Greg was saying earlier.
Yeah, we need to. I think, Jeff, at some point we need to get back to the Birch and Swinnerton Dyer because it's somewhat related to this.
It is, but no one has any errors in that one. No one's brought up anything with that one.
Yeah, that's another one that's Millennial Prize. There's a paper that Jeff put up, and
yeah. Well,
anyway,
you guys remember it too.
What I'm just thinking is that I think we can do a lot more graphically with that one as well. But
oh yeah.
That's for another day.
All right. Anything else you want to add?
No, this was great. Thanks.
All right. Thank you all. Good luck. $1,000. All right. Take care. Bye-bye.